Welcome back. Building on our earlier discussion of dry or chemical corrosion, we now move into the next major category, wet or electrochemical corrosion and its mechanism. This form of corrosion occurs in the presence of moisture or an electrolyte, and unlike a dry corrosion, it is driven by electrochemical reactions at the metal surface. In this section, we will walk through the underlying mechanism that govern how and why metals corrode in wet environment and explore the two key pathways, hydrogen evolution and oxygen absorption, that define this process. When metals are exposed to moisture or any electrolyte solution, they don't simply rust by chance. There is a well-defined electrochemical mechanism driving the destruction. This type of corrosion, known as wet or electrochemical corrosion, is the most widespread and a practically important form of corrosion encountered in engineering. When it comes to wet or electrochemical corrosion, it operates just like a galvanic cell. Two dissimilar metals or two regions of the same metal act as anode and cathode, with the electrolyte serving as the conducting medium. The anodic region undergoes oxidation and corrodes, while the cathodic region undergoes reduction and remains protected. Electrons flow from anode to cathode, and the metal is gradually consumed. What makes this mechanism particularly powerful is that it explains two distinct corrosion pathways depending on the environment. In acidic condition, hydrogen evolution drives the reaction, whereas in neutral or alkaline condition, oxygen absorption takes over. Understanding this mechanism is not merely academic, it is the foundation for every major corrosion prevention strategy, from sacrificial anodes to cathodic protection to corrosion resistant coatings. Yeah. Now let's move on to the mechanism of wet corrosion by hydrogen evolution. It's one of the two key mechanisms from the wet or electrochemical corrosion. As you can see in the diagram, when an acidic solution sits in an iron container contaminated with copper, the stage is set for galvanic corrosion. Since iron and copper are dissimilar metals in direct contact, they naturally form a galvanic cell. Consulting the electrochemical series confirms why iron is the one that suffers. Iron sits at negative 0.440 volt, while copper sits at positive 0.34 volt, giving iron the stronger tendency to get oxidized, uh, that means losing electrons, and copper the tendency to remain reduced, that does not undergo oxidation. In other words, iron acts as the anode and corrodes, while copper acts as the cathode and is protected. Since iron acts as the anode, the copper as the cathode, iron undergoes oxidation, releasing electron, where you can see the solid iron, that's a metal, which loses electron, then it becomes uh, iron 2 plus ions, and dissolving as Fe2 plus, while copper facilitates reduction at the cathodic surface. Electrons flow away from the acidic iron region, and the H plus ions present in the acidic solution consume those electrons and getting reduced to form the hydrogen gas. As you can see here, the H plus present in the solution that accepts the electron which was released from the iron, then it forms the corresponding hydrogen gas. Notably, because the cathodic area, the copper is the cathodic area, is relatively small compared to the iron, which are large anodic area. So the overall corrosion rates remains slow since the acceptance of electrons at the copper surface is relatively small. compared to the anodic region. They would release more electrons. However, acceptance would be restricted here, being the small in the cathodic region. This describes the classical mechanism of wet chemical corrosion driven by hydrogen evolution, which is characteristic of acidic environment. When the environment shifts to neutral, however, the mechanism changes. Instead of hydrogen evolution, the dominant cathodic reaction becomes oxygen absorption, where dissolved oxygen in the solution is reduced at the cathode, a distinct pathway that governs corrosion under neutral or near neutral condition. And overall, if you look at the diagram, you can see that the iron container, which contains a little bit copper impurity, where the iron container acting as an anode and losing the electron and becomes metal ion 2 plus, whereas the copper impurity present the iron container that becomes the cathode that facilitates the reduction of the H plus, that is the acidic species present in the solution that would accept the electron and becomes hydrogen gas. Therefore, it is very clear that the iron having the negative potential 0.44, negative 0.44 volt, that is the clear anodic region, whereas the copper being the positive 0.34, then it facilitates the reduction of protons. And the overall reaction, you can see that anodic region, the ion becomes ion 2 plus, whereas in the cathodic region, the H plus species is they are getting reduced into hydrogen gas. Yeah. Now let's move on to the another mechanism of wet or electrochemical corrosion, that is oxygen absorption. Now consider the same iron container, this time coated with an iron oxide layer and immersed in a neutral electrolytic solution under neutral or alkaline condition. The dominant mechanism shifts to oxygen absorption rather than hydrogen evolution. Here, the oxide film, what you can see here on the surface of the metal iron container, itself plays a critical electrochemical role. Any small crack or break in the oxide layer exposes bare metal, where you can see this region is a crack which exposes the bare metal, which acts as the anode, while the surrounding metal surface still covered by the oxide film acts as the cathode. This geometry creates a highly unfavorable area ratio, a large cathodic surface paired with a small anodic crack. Since the cathodic area is vast, oxygen reduction proceeds rapidly, driving an equally rapid oxidation at the small anodic site. The result is the corrosion is highly concentrated and accelerates quickly at the crack, making this scenario significantly more damaging than the hydrogen evolution what we have discussed earlier, because there the cathodic region is very small when compared to the anodic region. Hence, the acceptance of the electron is very poor when it comes to hydrogen evolution. Hence, the rate of the corrosion was bit slow when compared to this case. Here, the cathodic region is vast when compared to the anodic region. Hence, acceptance of the electron is highly uh, favored. Hence, the corrosion rate is very high for the oxygen absorption. So the overall reaction leads to the progressive formation of ferric hydroxide, commonly recognized, this ferric hydroxide, commonly recognized as rust. You can see that rust formation because of the uh, iron oxidation. As the crack continues to corrode and more ferric hydroxide accumulates, that's nothing but rust, the damaged compounds, making this oxygen absorption mechanism under neutral conditions particularly aggressive compared to hydrogen evolution in acidic environment. So overall reaction, when you look into this, rusting of iron in neutral aqueous solution of electrolytes such as sodium chloride solution in the presence of atmospheric oxygen, in the anodic reaction where iron is getting oxidized into iron ion and release of electrons. In the cathodic reaction where 1 by 2 oxygen plus water plus 2 electrons, that's leading to 2 hydroxide. It's a reduction. When it comes to overall reaction, the iron ion combined with the hydroxide that forms the corresponding ferrous hydroxide and subsequent ferric hydroxide, so that rust formation takes place. This is the another mechanism of wet or electrochemical corrosion. Thank you. Having seen the wet or electrochemical corrosion in detail, now let's summarize what we have gone through so far. Wet or electrochemical corrosion occurs when a metal is exposed to moisture or an electrolytic solution. And also, it's a most common type of corrosion often seen in engineering. This particular corrosion proceeds through an electrochemical mechanism similar to a galvanic cell type mechanism. And here, if you look at carefully, the electrons flow from the anodic region to the cathodic region. One has to remember this particular difference, anodic and cathodic reactions. Anode, that metal undergoes always undergoes oxidation and dissolves as metal ions. When you look at this particular equation, the M represents metal, pure metal, that would undergo oxidation and leaving as metal ion and releasing electrons. That is nothing but oxidation. Whereas when it comes to cathodic side, always reduction would take place. So corrosion always takes place at the anodic area and then it gets corroded, whereas the cathodic area remains protected. Now let us compare the cathodic reactions in different mediums, particularly in acidic as well as neutral medium. When it comes to acidic medium, there is always hydrogen evolution would take place, whereas in the neutral or basic medium, oxygen absorption would happen. And in the cathodic side, particularly in acidic medium, H plus, because one can see that a large amount of H plus would be present in acidic medium, that would get reduced to hydrogen gas. So therefore, one can anticipate hydrogen evolution in the acidic medium, particularly in the cathodic reaction side. Whereas we all know that in the anodic side, the electron would be released and metal would get oxidized. However, when it comes to the oxygen absorption mechanism that would take place in neutral or basic medium, the oxygen would get reduced in the corresponding hydroxide, OH minus. So that's because again the anode will get corroded and the cathodic side, since there won't be H plus, pH would be neutral or basic, hence oxygen would get reduced into OH minus because oxygen presence would be more in that particular medium. And the corrosion product, if you look at that, as we have discussed earlier, metal ions plus hydrogen gas in the hydrogen evolution mechanism. Whereas when it comes to the oxygen absorption, one can normally see the rust, that is in the form of FeOH thrice, ferric hydroxide. Again, this is very crucial when it comes to the area ratio. Whereas in the hydrogen evolution reaction, anode part would be very large when compared to the cathodic. The cathode would be very small, that we have discussed in the earlier slide, where large anodic area would be there in the hydrogen evolution reaction, whereas a small cathodic part. However, when it comes to oxygen absorption, that is in the neutral or basic medium, you have seen that there's a small crack that would act as a anodic site. That's why it's a small anode, whereas you will see the large cathodic area in the neutral or basic medium. Therefore, one has to remember this simple comparison, how the hydrogen evolution takes place, whereas oxygen absorption in the neutral or basic medium would occur. Thank you.